So if we look at considering some of in our previous lectures, in the past few weeks, we were considering some of the real life data sets and then trying to demonstrate how we can implement them in weaker environment. That is to really practicalize the modeling, starting from where you pick the raw data and then trying to see how the model work out. So if we remember, something that is unique to all is that often than not, we do have situations whereby when the data sets samples is not very much, however, the number of features are many. So we run into trouble of not able to get better results. So actually, this is often connected with this particular concept that is known as cost of dimensionality. It's like the punishment for having too much number of features. Because when you have a high number of features, then you are expected to also have a kind of appropriate increase in the number of samples in order to be able to do well or to be able to have a reasonable result from your modeling. So this is the concept we want to look at briefly for today's course. So what is cost of dimensionality? Cost of dimensionality actually stated that the required number of samples to achieve the same accuracy grows exponentially with the number of variables. So by this variable, they mean by the number of features. Now, so the idea is this, that usually when you are given, maybe your client provided you with data sample or data set. So you have number of features, X1, X2. So let's say we have X1, X2. And then you are provided with maybe how many samples? 1, 2, 3, 4, 5, 6. So maybe you are provided with like maybe 100 samples, as the case may be. See it? Or let's take it like this, that you are actually provided with one feature, just one feature like this. Let's look at this demonstration practically. You see? So you can see here, we only have X1. This is the number of feature. The number of feature here is 1, only one feature. And we are provided with 10 samples. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the 10 samples you have with only one feature. Let's say X1. Now, the cost of dimensionality is saying that the number of, if you run the experiment as it is now with just one feature and 10 samples, that the number of samples, if you increase the number of variables, let's say we say, okay, like someone contacted me recently, said, we only have only one feature. He said, is it possible to work? I said, let the data speak. So people would usually like to have at least minimum of 2 features. So when you increase the number of features by just one, the implication is you need to increase the number of samples also. But unfortunately, the increment in the number of samples you have to carry out is not going to be just by one. You see, if you increase the number of variables, even by one, you see, the required number of samples, if you want to achieve at least the same accuracy that you have achieved before, then you need to grow them exponentially. And if you remember, exponential growth is one of the worst scenarios anybody can ever face. Once you have an exponential growth, at a point you cannot manage it. You see, and this is exactly what the issue of cost of dimensionality is all about. See, so now look at this example. We have X1, only one feature. So during the training process, you have 1, 2, 3, 4. This 4 belongs to one class. 1, 2, 3, 4, 5, 6. This one belongs to other classes. It's a way to demonstrate this concept. Now, you can see that the plane has been divided into like 10 portions. So these 10 samples, hypothetically, is able to have a representative value inside each of these spaces. It means if a new sample is coming, if it falls to this place, then we know that it belongs to this class. If it falls to this place, it belongs to this class. So that it means your system is able to represent it, to have a system that can conveniently say, okay, we have mastered, we've understood the way this model should behave on the data set provided. Now, however, either by providence or deliberately, when you increase the number of features by just one, just increase the number of features by one. This is the challenge we face. You can see now, it become like X1 and X2. We have X1 and X2. Number of features now becomes 2. Number of features is now 2. Now, ordinarily, when you increase the number of features by just 2, you expect that, okay, we can increase the sample by just maybe 2 or so, 2 samples, but no. The problem is, now that our sample is now X1, X2, we need 10 raised to the power 2 samples. This is the big challenge. You need 10 raised to the power 2. You just increase the number of features from 1 feature here to 2, but now you need to increase the sample by 10 raised to the power 2 in order to be able to achieve the same accuracy that you had before. Remember that when we add only 1 feature, you can see each of these rectangle or partitioning has a representative value. To repeat that particular feat, when you increase the feature to 2, then you need to have every representation for this one because it's become 2-dimensional planar. So you have X1 here, you have X2 here. Unfortunately, the number of samples is still fixed. We still have the 10 samples we had earlier. Now, how are we expected to have the same accuracy? It is not possible. Because now this box now is there's no representation. We need we need a particular sample to represent each of these boxes. But now it's not available because the data set is not leveraging enough. So why don't we just increase the number of features also? Sorry, number of samples to 10 raised to the power 2, which is we need 100 samples now. But the challenge is the samples are not available. This is what the client has in stock, and they send it to you. See, sometimes we receive features like 17 features from the client with just 350 samples. With 17 features, ideally, we are supposed to have 17 raised to the power. Sorry, we are supposed to have 10 raised to the power 17 samples. But here you are provided with just 350 samples against 17 features. So this is called cost of dimensionality. Cost of dimensionality. That is, the number of features you have, it is a cost. Yeah, that's the remaining cost. It's a cost on the model you are trying to build. It means your model will not be able to scale appropriately. See? So this is just over 2. By increasing it to 2. Now let me increase it by even further, by another 1. Now I increase the number of features now to 3. And now this is what we face. You have X1, you have X2, you have X3. So with this, we are expected to have, you can see the number of spaces that are empty now. For every empty space here, you don't have a sample to fill, it's a big trouble for your model. You see, it's a big trouble for your model. We need to fill all the spaces, which means with 3 features, X1, X2, and X3, we need at least 10 raised to the power 3 samples, which is translating to like 1,000 samples. In order for your model to have the same accuracy that it had when it was having only one feature. Now, so when you are in need of 1,000 and now you could only get 350 from your client. So what do you do? So this is the big challenge that often face when you have modeling in machine learning. And that is what we refer to as the cost of dimensionality. Now, the required number of samples to achieve the same accuracy grows exponentially with the number of variables. See? So in order for us to, and unfortunately, almost all the algorithms, most algorithms suffer from this problem of cost of dimensionality, except extremely, maybe one of them that has been claimed not to suffer from this because it has a special way of handling things, and that is support vector machine. So one of these days, we hope we have the opportunity to demonstrate how support vector machine is able to avoid this problem or challenges of cost of dimensionality. And that is why whenever you have a very large number of features, of course, the samples are not always available to be able to speed up to. Even when you have 3,000 features, when you have 20,000 data set, and the number of features is maybe 25. So you are supposed to get 10^25 samples. Just you can do the calculation. That is a huge number of samples you are looking for. So even sometimes when you have 30,000 samples, but the number of features is really exorbitant, it is not go well. Because by 25 features, you are expected to have as much as keep adding the zeros. So it's going to be a huge number of samples you are looking for. However, in practice, in reality, sometimes the number of training example is fixed. This is why the problem is a very, very complicated one and a serious one. Sometimes the number of training example is fixed. You cannot increase them because the data doesn't belong to you. Even if it belongs to you, there's no way you can manufacture the data, except you just want to play around. So this data has been prepared by your client, and that is all they could get. They struggled, and then this is all they could get. But the number of features, there are so many. So therefore, one of the unique implications of cost of dimensionality is that the classifier performance usually degrades for a large number of features. So when the number of features is very large, naturally you see the number of variables, the performance. Look at this particular small graph. This is classifier performance. This is performance. It could be accuracy. It could be root mean square error. Whatever we have. Let's say this is root mean square error. Sorry, let's say this is a correlation coefficient or accuracy, how accurate it is out of 100%. You can see when you start here with maybe 1x1, you can see you have something appreciable. As you increase the number of features, you can see also it keep increasing when the number of features. So at a point, you keep increasing the number of features, subject to the number of available samples, you can see the performance can degrade. The performance can degrade. Because often, when you look at, because of the exponential increment in the required number of samples, usually you can meet it. Whenever you hear of exponential increment, it is usually difficult to satisfy. This is the natural way of the mathematical concept of exponential. When you hear of exponential growth, then if you can avoid it, then you need to avoid it. And that is why cost of dimensionality is a serious problem with the machine learning model development and other related concepts. Now, when you have cost of dimensionality, then so what is the way out of it? What is the way out of cost of dimensionality? Because in most cases, every algorithm will mostly suffer from this. And it's a very common thing you encounter every day. Maybe if you remember, maybe last week or 2 weeks ago, in one of our previous demonstration of data set taken from cargo, we can realize that at a point when we try to remove the number of features, then the performance improve drastically. You see, because the number of samples was smaller compared to the number of features that we have. So when we had like one feature, so with let's say we need like 10 samples for a sample. You have 2, you need 10 raised to the power 2. You have 3, x1, x2, x3, you need 10 raised to the power 3. And then it grows up like that. So when you have 10 number of features, 10 features, you are expected to have 10 raised to the power 10 number of samples, which in reality, the number of samples is always fixed by the client because this is what they can get. So in that case, what is the way out of it? So sometimes when you get your data, you start running your experiment, then you run into trouble. So you need to understand what could be responsible for this. So that's why first thing to check, the moment you get your data set is you see the very large number of features, then you should bear in mind that, we might run into trouble of cost of dimensionality. Because the moment the number of features are higher, then for sure, and the number of samples are limited, and they are bound to be limited. Yeah, because even when you have 5 features is not too much ordinarily. However, when you have 5 features, then you are expected to be looking at getting 10 raised to the power 5 samples, which is already a very big stuff. You're talking to 100,000 samples. Very rare to have a problem that have 100,000 samples. Very, very rare. So it means it's a very formidable problem to look out to. But the good news is with the appropriate implementation of what we call feature selection, you see, I leave feature selection as a solution to cost of dimensionality. So the natural solution to cost of dimensionality is feature selection. So we have to try to see for ways that how can we reduce the number of features? Since there are 2 things now that are competing, see, so the number of samples is competing with the number of variables or features. This is number 2. See, as you increase the number of features, you need to increase the number of samples, not just by 1 or 2, but exponentially, which we have demonstrated that it is something that is impossible for you to meet. Once you hear about exponential growth, then if you can run away, you need to run away or start looking for how you can manage the problem. Because for sure, you cannot get samples that will meet up exponentially as the number of features grows. So considering this, we've demonstrated it here. So how it is almost cumbersome for you to come by the number of samples that can satisfy you. So however, feature selection provides a solution to this huge problem called, often referred to as cost of dimensionality. And that is by trying to selectively look out for which of these features are actually contributing better to the model we are trying to build. So, and that's why feature selection is a very serious issue to look out for. So with feature selection, with appropriately deployed feature selection, then you can be able to solve the cost of dimensionality problem. There are several advantages of feature selection. See, for example, it could improve the performance of machine learning algorithm, for sure. See, because once you select the number of features, when you look at this, you say that as the number of features increases, see, as the number of, you can see as you increase the number of variables, there's possibility that the performance can degrade, can go down. So being able to remove unnecessary features. You don't just remove features, of course, at random, because you might end up, there are so many features available, but each of them, they have their own capability. They have contribution that they make. And that is why what we described, we had an earlier video where we described feature selection. There are different types of feature selection. You can actually refer to our earlier video on it, where we discuss several feature selection types that we can go on for. And there's so many of them. And then, as we described not long ago, that machine learning is not a dogma. It means which feature selection is the best. That question there's no answer for that. There's no feature selection that is best. You have to check. It's subject to your data. And that's why while we are working, always remember the principle, let the data speak. Let the data speak. So you might use feature selection of ordinary correlation coefficient. Just find the correlation coefficient between the input and the output. And then those features that had the highest correlation, you can select them. It might work for you. In another area, it might not be. There might be some features that are, if they are interrelated. You see, we might have feature X1, even though it has 0.96. Another one, X5, is having 0.25. Then while X2 is here with 0.92, you can say, okay, these two should give a better result, up not well. But sometimes when you combine these and these together, they could perform wonder for you. It means when they are together, they have a way of having a very unified synergy that can push up the modeling accuracy of your system. And that is why we have different types of feature selection. We have the univariate feature selection. We have the univariate. Univariate means we are going to be looking at the power of each feature one by one, like the correlation base. We see the correlation and then we rank them. Those with higher correlation, we use them, we select them as possible feature that might work for us. But in the multivariate in real life also, sometimes, as individual, if you work with another guy that is as intelligent as you might not achieve results. But sometimes you have a little bit less intelligent person like you work together in this very unique synergy, you get better results than when you work with your so-called highly intelligent colleague. This thing do happen. Either because you waste your time arguing, because it's not going to accept for you, you are not going to accept for him, you end up not getting something reasonable. But sometimes you have two people, they might be at different level of correlation, but when you match them together, they could perform some wonders. That is why sometimes we go for multivariate feature selection. But which one is better? Like I said, there's nothing that which one is better. You have to check for your data set and see which one works for your data set. It could be an optimization problem, looking for the best number of features and the actual feature that will actually give you the best possible result. So we say machine learning algorithms may not scale up to the size of the full feature set, either in sample or time. Sometimes it could be the timing, because if the samples also are available and they're huge, then in reality, your modeling and your algorithm is not able to model it in the reasonable time that is possible. Maybe even there is no machine that you can use to run it. So in which case, you need to bring it down. You need to reduce the number of features. So also feature selection as a solution to cost of dimensionality allow us to better understand the domain. See, with feature selection, you can be able to say, okay, which feature is working here? Okay, put this feature, remove it. Oh, this feature seems it's not contributing to this area. So then in it, you can document this. Others also can benefit. That whenever you want to model something related to customer churn, so attribute is not important. So people can take note of it. Of course, it again depends on where the data set has been taken from. The demographic distribution of data set actually goes a long way to also determine the performance of model that we are building, in addition to the features that are there. So some feature might not be important from some demography, while to some demographic data, it might be very important to them. Again, the principle of let the data set speak should always guide our decision making, so that we don't exclude what might actually be very good for us at the long run. Oh, because somebody last year, he worked on the data set on financial market analysis, he doesn't use this feature age, so we are not going to use it now. No, your case might be different. See? So let the data speak. Put all of them to it. Let everybody demonstrate its own power of contribution to the model by subjecting them to feature selection process. And then you can select the one that is actually contributing in reality. Also, when you have lesser number of features, we know that it is cheaper to collect a reduced set of predictors. So in addition to feature selection, helping us to solve the problem of cost of dimensionality, it also grants us the opportunity to have a cheaper set of features. If you have somebody, maybe I'm building a machine learning predictive solution for a medical problem, maybe diabetes, and I say, okay, people need to go and do medical tests of almost 25 medical samples. 25 tests, you need to do that. You see, this is enough to send away a lot of potential customer or participant in such experiment. It's too much. So even the number is scary. Somebody has a particular questionnaire. Hey, excuse me, can you help me fill the questionnaire? We have a very interesting project to do. Okay, I can quickly help you. The moment you see 25 questions, you might likely excuse the person. Oh, because I'm going somewhere. But if you can reduce the number of questionnaire to like 5 important ones, people will quickly respond to you by doing the test or by doing the questionnaire. That is another very unique advantage that feature selection brings to the table when it comes to modeling in machine learning, in addition to be the natural solution to cost of dimensionality. And also we say it is safer to collect a reduced set of predictors. So if you have to collect 25 blood samples, you know what that means to a patient that is just recuperating from a serious surgery. So there's a risk involved in collecting such a huge number of blood samples. So someone is saying, okay, we just need 5 samples or even 3 samples. So which it means it is safer, even if you have to go to places where there are risks that are involved in collecting some of these features. So the lesser the number of features, though, the lesser the risk that is going to be involved in the collection of such a feature. So invariably, meaning that in addition to feature selection being the natural solution to cost of dimensionality, it also has other potential advantages that it offers us, as demonstrated in a couple of our few weeks ago videos, whereby when we did feature selection, even initial step of feature selection improved the result drastically. So we have to take note of this. This is the concept that we refer to cost of dimensionality, that the moment the dimension of your data, especially the feature, is very high in number, then you can look forward that your algorithm might not be able to scale to the better modeling of that particular system, in which case we have to try to say, okay, what is the way out? Then the solution is the feature selection, or as the case may be. Then, in our, remember always the generalized machine learning model procedure. So this is where the cost of dimensionality solution might have to come. See, you might need to solve that problem here. You have the data set. First of all, do your data modeling, select the algorithm, check the performance. Oh, the performance is not good. What could be responsible? Perhaps the number of features are many and the number of samples are very small. Then you have to go back again and then try to see, okay, can I do feature selection to solve this problem of cost of dimensionality, so that we can hopefully improve we can improve the output of our models, or as the case may be. So this is a short description or demonstration of cost of dimensionality that we're going to have for the day. So we're going to give room for clarification or question from the audience, if there is any, before we call it a day. Thank you very much for listening. And if you have a question, we can take a couple of